We have now seen the generic 6 steps of Gaussian probabilistic inference, and we're going to use these 6 steps ultimately to come up with a methodology to estimate the state of our battery cell. And we do this in a few steps. The first step is to use the general solution as a basis for deriving the linear Kalman filter. And the linear Kalman filter is not itself going to be especially useful for estimating a battery state because a battery model is not linear. But I believe that the insight we get by doing the derivation for the linear case will be helpful when we get to the nonlinear case as well. And we're going to get some insight and some intuition, I hope, from the linear case. We will actually do a state estimator for a battery cell using the linear Kalman filter, but in order to do so, we're going to have to greatly simplify the battery model to the point where it would not be very useful in practice, but it will at least give you some idea of how the Kalman filter operates in practice. So over the rest of this chapter, we're going to derive and implement and look at results from the linear Kalman filter, and then similarly for 2 different types of nonlinear Kalman filter as well. So a linear system has a state space form of xk equals ak minus 1 times xk minus 1 plus bk minus 1 uk minus 1 plus wk minus 1, where x is the state, u is the input for us, that would be battery cell current, and w is a process noise, so it's some unmeasured signal that does influence the state somehow, but it does not is not measured. And then we have the output yk equals ck xk plus dk uk plus vk, and vk is a sensor noise that does not influence the state. That's the primary distinction between w and v, is that v is simply a corruption of the measurement, whereas w furthermore impacts the state itself. A, B, C, and D are matrices of numbers, and at any time step they are constants, but by the subscripts we put on the ABCD matrices, we indicate that it's possible for the matrices to change value from one time step to another time step. With that reminder, let's go through and see how to derive the Kalman filter. With what we've done so far, this is fairly straightforward, and it amounts to algebra more than anything else, which is a lot easier, I think, than calculus and difficult derivations. So we go through the 6 steps. So step 1a, generically speaking, said we need to be able to compute this. We compute a prediction of the present state given the state equation and all previous measured outputs. So F, remember, here is the state equation of the model, and we have just rewritten up here, this is the state equation of the model when we have a linear model. So I substitute F to be ax plus bu plus w, and we have the expected value of all of that given y. A very important property of the expectation operator is that it's linear, which has basically, it says that expected value of alpha times random variable x plus beta times random variable y is equal to alpha times expected value of x plus beta times expected value of y. It obeys the superposition principle, so I can break up the expectation of a sum to be the sum of the expectations, and the expected value of a constant times a random variable is equal to the constant times the expected value of that random variable by the linearity. We take advantage of this in a couple of steps here. So notice that what I'm trying to evaluate is the expected value of something plus something plus something, and we break that up into expected value of something 1 plus expected value of something 2 plus expected value of something 3. That's because of linearity of the expectation operator. And then, because the A, B matrices are known constants at any value of time, any point in time, I can write this, for example, as AK minus 1 times the expected value of XK minus 1 given YK minus 1. The constant comes outside of the expectation, and I can do the same thing for that. We recognize by definition the expected value of the state given at some point in time, given measurements up to and including that particular same point in time, is what we call the estimate of the state at that point in time. So that's an x hat plus quantity, and the point in time is k minus 1, so it's x hat plus k minus 1. The U signal is a deterministic signal in the sense that it's measured. It's not a random variable. So the expected value of something deterministic is itself. So I simply write that as B times U then. And finally, we have said that we are assuming the noise process W is zero mean, so the expected value of W is 0. So a couple things. One, when we're working with expectations, even though a few sections ago we defined them as ugly integral expressions with probability density functions and so forth, when we implement when we do math with expectations, most of the time, at least for us, we're going to find that we never ever have to implement that integral. We just take advantage of the properties of expectation being linear, and that allows us to do algebra with them. And that's going to be common this whole time. Second thing to note is the general probabilistic inference solution for step 1a was this, which is not something I can implement in a computer code because of that expectation operator. There's not a command that says find expected value of thing. We need to be able to expand that out or simplify it and write it in terms of what that thing really means. And so that's what we're going to have to do for all the Kalman filter variations we look at. And for the linear model, we find here that we implement the prediction as this equation right there, and that is something that we can write a computer program to implement. In MATLAB, it's simply x minus equals a times x plus added to b times u. It's one line of MATLAB code. If you have to implement this in a lower level language like C, the matrix multiplies require a little bit more attention to be able to compute them. However, it's still extremely computable. This is, at this point, it's not a problem mathematically. It's simply a matter of figuring out how to write code to implement this mathematical equation. So the prediction of the state right now is accomplished by taking the estimate of the state at the previous time step and propagating it forward in time using the state equation of the model with the best possible assumption, the most reasonable assumptions. We're assuming that 0 times W, that the noise is equal to its mean. That's the best we can assume. That's the most we can assume without actually being able to measure the noise. We say, well, the mean is the most likely value, if you will, or the center. So that's what we will assume there. We measure the inputs, so that part is deterministically propagated through. And my best guess of what state to propagate through the equation to get the present state is the past estimate. So again, trying to be careful with nomenclature. We are predicting a present state because we're not using data up until the present time. We're using only past data. So when we're predicting, the best we can do is to use the most recent estimate from the prior step and the model, and we propagate the mean, in other words, that state estimate, forward in time. That's step 1A. Step 1B says that we want to find sigma x tilde k minus, and that's equal to expected value of x tilde k minus times x tilde k minus transpose. To be able to evaluate this mathematically, I benefit from having a simpler expression for what x tilde k minus is. So let's look at that. By definition, it's the true state minus the prediction of the state. And the true state minus the prediction of the state is there. The true state is this. We are assuming that our state equation is in fact correct and precise. So the true state is ax plus bu plus w. And our predicted state from before is equal to this. Of course, this was a plus, but it's minus here because I'm subtracting it. When I do this subtraction, we have a b times u, and we have a minus b times u. And those cancel each other. And then I have an a times x minus an a times x hat plus. And we remember that x minus x hat plus is what we call x hat tilde. So when the dust settles, everything is combined. We have this expression where the prediction error, I said estimation error, but more correctly prediction error, is equal to a times the previous estimation error plus the process noise. So the covariance of the prediction error, I start out with the definition of what the covariance is, and then we will substitute into that definition this expression there and there. Which we do right here. So I have ax tilde times a plus w times ax tilde plus w all transpose. Now we are going to FOIL carefully, remembering that when I transpose things, that reverses the order. So generically, wx transpose equals x transpose w transpose. We must remember that. But let's go through and do this term by term. So I have ax times ax all transposed gives me ax times x transpose a transposed when that's worked out. And then it looks like I did w times ax all transpose gives me w times x transpose a transpose. And then I think I did ax times w, and that gives me ax times w transpose, and finally w times w transpose gives me that term right there. Now there's a few lines missing here, which I think I will do on this side, at least this one time. We can take advantage again of linearity of expectation to write all of this as ak minus 1 times expected value x tilde k minus 1 plus x tilde k minus 1 plus transpose times ak minus 1 transpose plus expected value of wk minus 1 x tilde k minus 1 plus transposed all times ak minus 1 transpose plus ak minus 1 times expected value of x tilde k minus 1 plus w transpose k minus 1, finally plus expected value of wk minus 1, wk minus 1 transpose. So just the linearity of expectation allowed me to do this. What we have here is I have A transpose, and in the middle, expected value of x tilde transpose, by definition, is sigma x tilde plus. So all of that term becomes this right here. Then at the very end, I've got expected value of w, w transpose, and that is, in the first step, we would write that as sigma w, k minus 1, and then recognizing that w is zero mean, the correlation is the same as the covariance, so I can put the tilde on top, and that gives me that term right there. And then one of the assumptions that we made when deriving the Kalman filter was that the present noise and the present state are uncorrelated with each other, because if we go back up to the state equation, we find that the present state depends on the prior noise, not the present noise. So just looking at the indices here, these are at the same time, and we've assumed that they're uncorrelated. So to take one of these terms right there, we can write that because they're uncorrelated, we can write it the expectation of the product as a product of the expectation. That is not true in general. Linearity of expectation does not allow us to do that. It's the uncorrelation that allows us to do that. So this term becomes expected value of wk minus 1 times expected value of x tilde k minus 1 transpose, all times a k minus 1 transpose. And when we're looking at that, we say, oh, but w we've assumed is zero mean. So if that's zero mean, that goes to 0. The whole thing gets multiplied by 0, and that entire term goes away. Similarly, the same process we do with this, and because w is zero mean, that whole term goes away. So those disappear. And we end up overall with this result here, and this result is for sigma x tilde k minus. So we have updated the uncertainty, the covariance matrix, from the uncertainty. We started with the uncertainty of the previous estimate, and this is now the uncertainty of the present prediction. And we can gain some intuition from the math of what's really happening here. First thing is, if we have a stable system, the A matrix is contractive, which basically means that your state is collapsing towards 0. And if I have some state versus time, it might be here, but it's collapsing towards 0, or here, collapsing towards 0, or here, collapsing towards 0, or there, collapsing towards 0. The main point is that over time, the uncertainty is getting smaller. So this first part here is what's happening to the uncertainty simply due to the passage of time. If the system is stable, the uncertainty is getting smaller. If the system is unstable, the uncertainty is getting bigger. If the system is marginally stable, then the uncertainty is staying the same. In our battery model, the diffusion states are stable, so they're getting smaller. The hysteresis state is stable if I am doing something with this cell, and it's marginally stable if I'm resting. So if I'm doing something with this cell, the hysteresis state should be getting more certain. If I am resting, the hysteresis state uncertainty should stay the same. And the state of charge is marginally stable, meaning that the propagation of time does not help me determine state of charge. The uncertainty remains the same. So that's the first term. The second term is the addition of uncertainty due to the passage, well, not the passage of time directly, but the process noise impact over time. I don't know what that W variable is, and it is affecting the state, and so it is adding uncertainty to this state, until I'm able to make some measurements and correct for it, but simply predicting into the future, the uncertainty of the state gets higher because of that sigma w term. So overall, for us, this term is driving uncertainty down or staying the same versus time. This term is driving uncertainty up, and there can be a steady state solution that kind of balances things out, and we'll think about that a little bit more in the future. So I hope that you're seeing that these equations are not simply mystical algebra, but there is some insight to be gained into how the filter is intelligently operating over time. Also, once again, maybe you'll get bored of me saying this, but this is an equation that I can implement. If I have the sigma covariance matrix from the prior estimate, I pre and post multiply by A, and I add my sigma w. These are completely computable equations, and so step 1b is something I can implement in one line of MATLAB code. Step 1c says, generically speaking, that we want to estimate, or predict might be a better word, the system output as this. And the output equation, remember, is yk equals ck xk plus dk uk plus sensor noise vk for a linear system. We take the generic output equation and replace it with the specific linear output equation of our model. And then we take advantage of linearity of expectation. This is a summation of terms of term 1, term 2, term 3. And C and D are known matrices, so they come outside of the expectation. The first expectation then becomes C times expected value of xk given yk minus 1. That's a prediction because that's a previous time step, that's a present time step. So C times x hat k minus. U is measured, so it's just D times U. And we have said that sensor noise is assumed to be zero mean. So expected value of V is 0. That goes away. Again, a very computable equation for predicting the measurement before we take the measurement from our system. So this is our best guess of what the measurement will be, and the best we can do is to predict the output given the output equation, the system model, and our best guess of the system state at the present time. Step 2a, we've done all of our predictions. Now we are going to make our corrections, and we have to prepare for the correction by computing the estimator gain matrix, which is also known as the Kalman gain matrix. The equation to compute the gain matrix is this. L is equal to the cross covariance between x and y, x tilde minus and y, and the inverse of the autocovariance of y. We have to find those two matrices. Let's figure out this one first. We start by saying y tilde equals y minus y hat. Y from our model is cx plus du plus v. Y hat is cx hat plus du, and we're subtracting. And we've seen something like this before. The du and the du's subtract out, they cancel out. And I have a c times x minus c times x hat minus. So x minus x hat minus is x tilde minus. So all of that together gives me c x tilde minus plus v. We use this to compute sigma y tilde, which is the expected value of y tilde times y tilde transpose. And the mathematical steps are basically the same as what we saw for step 1b. We use FOIL first to expand this out. So CX all transposed, V times CX all transposed, CX times V, and V times V is there. And we use the linearity properties, and we use the uncorrelated properties of the process noise being uncorrelated with the state, and we get this equation here, which is the same basic form as what we saw in step 1b when we were computing the autocovariance of the prediction error. And we can then also use our result up here for what y tilde is to find expected x tilde y tilde transpose. There's our y tilde. And we multiply that out. It's not a FOIL anymore, it's simpler than that. So it's x times cx all transposed, and x times v transpose gives me this. And the state and the prediction error, not the state, the process noise, sensor noise. The sensor noise and the prediction error we are assuming is uncorrelated, so those break apart. Sensor noise is zero mean, that part goes away. This part here, notice, is expected value of x times x, and the c is a constant. It comes outside of the expectation. X times x, expected value is sigma x, so I have that result right there. Putting everything together, we get this equation here for the Kalman gain. And that, again, is completely computable. We know the C matrix, we know the sigma x tilde minus from step 1b, and we know the sigma v as part of our model of the system that we're estimating. And believe it or not, there's a lot of insight that we can get from this equation. It might look very daunting, but it's actually not if you break it apart into little pieces. So let's do that. The computation of this Kalman gain is really the most critical aspect of Kalman filtering that distinguishes it from other estimation methods. There's other feedback methods like Leuenberger observers, and there's various different things that could be used to estimate a state, but the Kalman filter is optimal, and what makes it optimal is how we are computing this gain. We want a good filter, we want an optimal filter, so we compute this gain carefully, and we note when we derive it, there's the computation. The only, well, not the only, but because this computation includes these covariance matrices, that is a requirement which causes us to have the step 1b and 2c that compute covariance matrices. It's nice to have the covariance matrices because they give us error bounds on our estimate, but we don't have to compute these covariance matrices if we don't want a Kalman filter, but we need them because we want this time-varying gain L that's optimal. So maybe not the whole reason, but that was at least the primary reason for computing the covariance matrices, because they're needed here. So L is time varying, and it is adapting over time to give us the best estimates of the state that we can get based on present conditions. How do we use L? We use L to say later on that we take the prediction of the state from step 1a, we take the prediction of the output from step 1c, we measure the actual output. This difference here is the part I wasn't expecting. I thought that it would be y hat. In fact, it's not. It's y. There's a difference, and so that's called the innovation, because it's new information somehow to me, and I want to blend this new information in with the old information in my prediction, and L comes in as the blending factor. This is the optimum gain or optimum blending factor that converts my prediction into an estimate that uses the actual measurement as well. So that's the purpose of L. If I have a very, very small L, I'm thinking kind of qualitatively rather than quantitatively, because L is usually a vector, and it gets a little tricky to think of big vectors and small vectors. But just thinking generally, if L is a really, really small valued vector, then we are making very, very small updates, and our prediction was the best, almost as good as we could do, is what we're thinking. Or if L is really, really big comparatively, that means that maybe our prediction wasn't very good, and we're trying to take the most information that we can out of the measurement y to update that prediction to make an estimate. So big L, small l has to do with how much we're updating the prediction to make an estimate. Breaking L down, we're thinking of L here in two parts. This is the first part, and then this is the second part. So the first part is the cross covariance between x and y. And that's this. And it indicates the relative need for correction to x, as well as how much information the output measurement contains regarding the individual states in x. And we see that in the linear filter by the form of how we compute that matrix. So the first part, sigma x tilde, that's the uncertainty of the prediction. If the uncertainty of the prediction is large, that means I don't really have much of a clue of what the state is, so I probably would like to have a large update based on the measurement to get a better idea of what the state is. So sigma x tilde being large, leading to L being large, has some sense to it. However, we also multiply by the C matrix. The C matrix is the coupling. Remember, y equals cx plus du plus v. The C matrix is the coupling between the measurement and the state. And if, for example, the C matrix had some zero values in it, that would say that some particular state is not directly coupled to the output, and therefore I would not want to have a large update on that state due to the output, because there's just no direct relationship. But if the C matrix does have a large number in it, that says, oh, this state has a big impact on the output, and if the output error was large, maybe I need to correct this state a lot to help correct what I see there. So C is the connection between state and output, and sigma x is how bad the state prediction is right now, and the combination is helping to tell us how big should L be. And I think that's what I'm saying here, basically. The second component in the L is sigma y inverse. So sigma y, not inverse, tells us the uncertainty of the measurement error. Not the measurement itself, but the measurement error. And so it's y minus y hat. Now, there could be a big error there because I know my y hat is going to be bad because I already know my x prediction is bad. So that's one reason why we might have a big measurement error. And another reason might be that there's a lot of sensor noise, for example. So if sigma y is large, I really can't tell if the measurement error, the y tilde, is due to the fact that I'm not very certain about my state or because there was a lot of measurement error. So I want to be careful. If sigma y is large, I want to have small, slow updates until I can make sigma y smaller. But if sigma y is small, that means that I'm really confident. I have a reasonable confidence in my state. I've got a reasonable confidence in my sensor because there's small errors. So overall, I believe that this innovation is going to be very helpful in updating my state, so I want to have a relatively big update. So instead of multiplying by sigma y, I divide by sigma y. So if I divide by a big number, I get a small number. So if I have a large sigma y, that's going to give me a slower update, a smaller L. And if I have a small sigma y, I'm going to have a faster update, a bigger L. And the form of sigma y says I've got this part, which is how the prediction error contributes to error in the output estimate. So if I've got a lot of state prediction error, I can't necessarily be too sure whether the output error is due to a bad state or a sensor noise, so I'm a little bit more cautious. Or if my sensor noise itself is large, then I also need to be cautious with my update. Hopefully that's helpful. The L Kalman gain is not mysterious. It's saying, how uncertain am I about this state right now? Relatively speaking, if I'm very uncertain, I would like to have a large update, all else being equal. If I'm very certain, I want to have a small update, all else being equal. But if the sensor is not really connected to the state, then that particular state I don't want to be updated by this process. It is updated, by the way. It's updated in the prediction. So we don't have to worry about the state never being updated. It is through the model equations, but it's not updated directly from the measurement. And then we are also scaling by how much sensor noise and so forth is in the innovation. So how good we think the innovation is, how beneficial we think it is as an update input. We now go to look at step 2b. Step 2b is always the same for all types of Kalman filters, and it's this. We made our prediction, step 1a. We made this prediction, step 1c. We made the Kalman gain, step 2a. We made a measurement somewhere, and just do that computation, and we're done. So the variable y hat is what we expect the measurement to be based on our state estimate at the moment, and y minus y hat is what's new, and we call this the innovation. And we use this new information to update our prediction, being careful to weight it according to the Kalman gain. The final step in our Kalman filter is the error covariance update for the measurement. And this here, again, is something that we figured out in the generic sequential probabilistic inference to be this. And there's a number of different ways of implementing that equation. You can go through these steps here and find out that this is equivalent. In fact, this one here might be slightly better numerically. And there's an even better one numerically that we won't go into in this course, but it might be useful if you're doing more general Kalman filtering. The intuition behind this step says I had a prediction uncertainty and I have made a measurement. How has that prediction uncertainty changed in my estimate? What is my estimate uncertainty? And it should be smaller. There's information in the measurement. No matter how noisy the measurement might be, there should be some improvement between the prediction and the estimate. Now, in terms of matrix algebra, the covariance matrices are always positive semi-definite. You could think of this as positive or zero uncertainty, but never negative uncertainty, if you want to think about it that way. So this product, that here is always positive semi-definite. This product here is also always positive semi-definite because it's a symmetric product. So I'm subtracting, if you will, at least intuitively, a positive number from a positive number. So I've got this positive thing, and I'm subtracting this positive thing, so what I end up with is always smaller. And because the covariance matrix is always positive semi-definite, I end up with something that's, this here is by mathematical necessity always positive semi-definite as well. So I still have uncertainty, possibly. I don't have negative uncertainty, I still have uncertainty, but it's smaller than it was. The estimation error uncertainty is smaller than the prediction error uncertainty, so it's better. Numerically, you can run into problems due to round-off error with this becoming non-positive semi-definite, and that's a concern. There's things that we can do about that. I don't remember if we talk about them in this course or not, but the Common Filter course, if you go over and you look at the corresponding notes and videos for those lectures, there's some ideas that we talk about there. So that is the derivation of all 6 steps of a linear Kalman filter. If for some reason we miss a measurement because a sensor faulted temporarily, or there was a communication issue between the sensor and my battery management system processor or something like this, then all is not lost. We simply do the prediction steps, 1A, B, C, and we skip the update steps because we don't have any information with which to make the update. So we set L to 0, we set x hat plus to x hat minus, and we set the sigma x tilde plus to sigma x tilde minus. That's very convenient because there are places where we can see, where we can determine that there are in fact skipped measurements or bad measurements, and this allows us a very robust solution to deal with that. And repeating one more time, the estimator output comprises 2 chunks of information. One is the state estimate itself from step 2B, and one is the covariance estimate from step 2C. And we have high confidence that the true state lies in these bounds right there. So that's a bunch of math. I'd like to spend some time next visualizing this, if possible, with a battery cell model. And we'll do some things by hand, and we'll look at some program results and so forth. And hopefully this will give you a feel for how the filter operates in practice.